So no questions on this. So what does the backward view do? Let me do it here. So backward view uses something like this, right? So I said these were all stimuli, right? But we are not talking about stimuli now. We are just going to talk about states, right? So whenever a state occurs, okay, let us say some S1 has occurred here, right? I increase the eligibility of S1. Okay, I introduce this new variable called eligibility. I will increase the eligibility of S1 and start decaying it, right? So here some state S2 occurred. S2 occurred again here. So I increase eligibility of S2, I increase eligibility of S2 and I keep decaying it, and whenever some reward happens at this point I will update every state according to how eligible it is to receive an update.
We are decreasing all of them by the same amount.
All of them by the same rate.
And when you do is the initial increase more and the subsequent increase is less, or it's all?
No, right now I am just increasing everything by 1. I mean that is a option, you could use how much ever you want to do, right. So this is 1 and this could be whatever, this should be 1. Right. So here they show you a hedgehog like picture when a state occurred multiple times. So it just keeps going up, 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 up. So what I am going to do is I am going to introduce this new variable called eligibility, right. I am going to say there is one for each state, right. The eligibility of the state is equal to gamma lambda times the previous eligibility, that is the decay part, if it is not the current state. If it is the current state, start off with all eligibilities as 0. So the first time I visit a state it will go to 1 and then from there it will start decaying. Okay. So this kind of representation is called we call this accumulating traces because it just keeps on accumulating the eligibility as and when you revisit the state, right. There is also a version called replacing traces, which essentially that is replaced by So how will the replacing trace thing look like? So a state occurs here and it occurs here again. So here it will go up, it will start decaying, it will go up, it will start decaying, right. When it goes up the second time it will go up to 1, okay, it will not go beyond. So it essentially takes the old trace and replaces it with a new trace, okay. So this is called replacing traces. So the first part is the same. If it is not visited you will decay it, if it is visited instead of adding 1 you basically make it equal to 1, okay. This is accumulating, this is replacing. It turns out that, okay, let me write this. So let me define delta t as small delta t, okay. This is the TD error, we saw this, right. This is a TD error. am going to define capital delta T, right, this one, no sorry, no, not delta T, capital delta equal to alpha times so every step I am going to change the value of state S, right, or at least I am going to compute a change in the value for state S, right. Notice that the delta T is only time indexed, it is not state indexed, right. At time t whatever is the current state, based on that I am going to compute the delta T, whatever is the current state, whatever is the next state and whatever is the reward, I will compute the delta T and use that same delta T for changing the values of all the states, right. Why does it make sense? Some sense, this delta T is where your current reward enters the picture, right. So whenever I get a reward here, I will use the current reward and I will change all the states which have a non-zero eligibility at that point, right. So that is essentially what is happening here, but we have to show that all of these pesky components here will all get telescoped into one another and you will end up computing GT lambda. Okay, so that is the cool part about this, right. So now you can see how we can have an online versus offline version. So online version is as soon as I compute that delta Vt of S I will apply it. Offline version is I will wait till the end of the episode, add up all the delta Vt of S and then I will change it one go, right. So now I can now in the backward view I can have an online and offline version, and so that is what the graph in the picture is. In the old edition they do not have a picture for the online version, I think, no they do, okay fine, yeah they do it after they describe the online algorithm. Okay, so the online version, yeah, here also 0.6 is the minimum, not 0.8. It is the same graph I think. 0.8 and 0.6 both are there, but 0.6 is lower than 0.8. 0.8 is lower than 0.6, Aha. You know why? They do not have 0.6 in this graph at all. So it is the same random walk problem. So I was really surprised when you guys said it is different, but yeah. So they basically generated it for different steps of lambda. Okay, so here they did it in steps of 0.2. So you go from 0, 0.2, 0.4, 0.6, 0.8 and so on and so forth. But there they have done some arbitrary jumps, so there are no 0.6 there. Anyway, so great. So what would your TD lambda algorithm look like? It looked like just like your TD algorithm. In the TD algorithm, if you remember, I update the value of the current state I am in, right, or the current state. I am in ST, I do an action, I get ST plus 1, then I compute the delta and I change the value of that state, right, the state I was in before making the transition. Here what I do the same thing, I come to a state, I pick an action, I perform the action, I get the next state, I compute the delta, then I update the eligibility trace, right, I update the eligibility trace, right, for all the states, right, I update the eligibility trace for all the states and then I update the value function for all the states and then I keep going, right, till I come to the end of the trajectory, right. If I am doing the offline version of this, I will compute everything, but I will not update the value function, I will just compute my change in the value function for that instance, I will keep adding it to my I have an accumulator, I will just keep adding that. At the end of the episode, I will take everything and make one update to the value function.
So shouldn't we make the eligibility trace 0 after some time?
Why?
Maybe the current reward is only depending upon the last 2 or 3 traits, not more than.
And have it decay very quickly.
The accumulating traces keeps on increasing, it's unbounded.
Mm.
So we need to bound it within a certain value.
Yeah. You might have to. So there are multiple things here. So if you can make sure that your eligibility trace would decay sufficiently before your expected return time to the state, right, then you are safe. I mean, there are a whole bunch of different things you have to take into account here. And if you choose your lambda such that it decays very quickly, right, if you suspect it is not going to be more important than more than 1 or 2 steps into the future, then your lambda should be very small. Right, so very quickly it will decay to 0 or close to 0, right. So there are a whole bunch of other tricks. So another reason you would want to make your lambda 0 is because of efficiency in computation. If you have a very large state space, right, I do not want to be updating the eligibility trace for every state in every step I take, right. Every step I take I have to keep updating this eligibility trace. So if at some point if you make it 0, then that will be efficient. Right. So all I need to now do is have a mechanism for keeping track of the non-zero eligibility traces. So if I have a fast way of accessing the non-zero eligibility trace, I can only update the values for those states, and whenever it comes below a certain threshold, I can make it 0.
So is it possible, so let's say if you are using replacing traces, so is it possible for us to think of the ET as some sort of a probability and update the values probabilistically? So let's say your ET is 0.9, then you'll update the value of that state with probability 0.9 using the current reward.
Why would you want to do that?
That the responsibility of that state for this current reward is about 0.9, and maybe I'll only update it with probability 0.9.
Why do you want to have that interpretation? Why you think that's a reasonable thing to have?
Because if there's some kind of very random moves that the
Wouldn't that happen over multiple trajectories? So this trajectory it occurred, next trajectory it might not occur. Right? I mean, so if you say there is a random possibility of it happening or not, right? If at every trajectory I come, right, I see this, and a little while later the reward happens, right? Shouldn't it get some benefit for that? But every time you will still be considering it as only 0.9, right? So just because you can squeeze the number to 0 to 1 doesn't mean there is a valid probabilistic interpretation for it, right? So I'm not sure there is a valid probabilistic interpretation for that quantity, right? There might be other ways of coming up with a stochastic update, but just not looking at the decayed value of the trace. Okay. So any other questions on this? Okay. So a couple of observations to make. So what happens to my lambda return if lambda is 0? Yeah. So are you convinced that it becomes TD 0? Only GT1, right? So everything else will vanish, right? So if I make lambda 0, I get TD 0. So we are all so it's fine to call that algorithm TD 0. What happens if we make lambda 1? Right? So don't look at this. If you look at this, then it makes a 0, right? But look at this, right? The first term will go to 0 if lambda is 1. All you will be left with is GT. Huh? Was it a full return, right? So it becomes Monte Carlo. So what is the amazing thing about the TD lambda algorithm? I can implement this with lambda equal to 1. Right? So I have a incremental way of implementing Monte Carlo. Right. So earlier you were saying Monte Carlo algorithms you have to wait till the end because you need to get the whole return, but because of this backward view interpretation, all I need to do is implement this with lambda equal to 1 here, right, and it will give me an incremental way of doing Monte Carlo updates. In fact, it gives me a way of doing Monte Carlo updates even for infinite trajectories. So should we do it? On what? Huh?
How large the trajectory is?
Huh?
How large the trajectory is from the
I
base?
said infinite. Non-episodic tasks. Come on. Huh? Depends on what? What is the problem with implementing it for long infinite trajectories? It could go. I'm sorry? Yeah, I'm not talking about infinite state spaces, I'm just talking about infinite trajectories. Yeah, infinitely long trajectories.
Too large.
It can be too large, so what? ET values can become really small, yeah. So then you can think of zeroing it out or something. Just make sure your gamma is not very large, man. I mean, or gamma is 1, you are doomed. Right? So in episodic tasks, you can implement Monte Carlo problems with gamma 1, it's fine. But if I am going to do TD lambda with lambda equal to 1, I have to make sure I have a non 1 gamma. Otherwise, if the trajectory runs infinitely, then my rewards will blow up. Okay, so that's simple thing. Okay, good. So we know the special cases, we have looked at the special cases. Okay. So let me so I have to do the equivalence of forward and backward views of TD lambda, which is not there in the new book. They took it out. Because it's very cumbersome, I mean you just do page after math. So very simple dumb math actually, not even very clever stuff. Okay, here is my way of getting back at you guys. Go read the first edition of the book, read section 7.4. Okay, that asks you to establish the equivalence between the forward and the backward view of TD lambda. Okay, saying that essentially if I do updates like that, I compute this thing, right, and it's offline equivalent because this is the offline return, this is offline, so I shouldn't be looking at the online updates, I should look at the offline updates. Essentially I have to accumulate all the delta VTs, right, that I will make in a single episode and show that that's exactly equivalent to this. Okay, so it's very simple, it's just arithmetic, it's just counting, right. So it's very cumbersome counting, and since none of you want to read the book, I am forcing you to read the book, and I will ask you a question on this. Huh? Whenever the exams come, so you will have to remember that. So you better look at it now, right. I will have to remember that. Or maybe can we just push the exam syllabus till today? Huh? The exam date today, is it? Oh, push, no, exam date is not getting pushed. So, sir, I can ask you this nice question. No?
But you said it's just math, simple math.
But I will ask you something that asks you to use the math in a more interesting way. Maybe I should even tell people what the question is because it's a pain even then. Right? So he was asking about zeroing out eligibility traces after a while. So that is the backward view, right. So what is the forward view of zeroing out eligibility traces after a while? it's non-trivial. I usually give this only in take-home exams. Don't worry, I will not give this in in-class exam. Okay, so I will ask you a different question in the in-class exam, but this is non-trivial. So what is the forward view of eligibility zero? So keep it very simple. Let us say I am going to be very drastic. I will zero out eligibility trace after 3 steps. I don't care how much it has decayed. I will zero it out after 3 steps. Okay, this is the backward view. So essentially, if st not equal to s, I will decay this, right, once, twice, thrice. So I had to keep a count, right? How many time steps have elapsed since I last encountered the state, right? I will zero out the eligibility trace. That is a backward view. So what is the equivalent forward view? To solve that, you need to figure out how we do this arithmetic to establish the forward and backward equivalence. So you will have to read that up and then figure out, okay, from there how do you derive this, okay. So Varun, can we add that as the homework question for this chapter? Okay, good. So you must have the wordings, right? I asked it in one of the earlier exams. Last year in sim. It's a take home, right? Yeah. So you can. So it takes too long to solve in class. Yeah. I don't think anybody got it right also. Take home. Okay, good. What is the other thing I wanted to mention now? So let us take TD1. Okay. So we looked at 2 different variations of Monte Carlo, right? What are the 2 variations? First visit and every visit, right? Yeah. So first visit and every visit. Yeah. So off policy eligibility trace is a little tricky, right? So we will come to that. Not much work has been done on off policy eligibility traces, so we will have to come to that. In fact, very recently there is some work on something which they call true TD lambda or exact TD lambda or something like that, because TD lambda, right, the forward view talks about the offline updates, but almost always when TD lambda is used, it is used in the online fashion. Okay, nobody uses it in the offline fashion. So the equivalence of the forward and backward view has been established for the offline case, but in the online case the forward view is no longer that clean. Right, you can imagine, right? Online case, I keep changing the return as I go along, right? So I keep changing this delta t, right? This VST that I will use here, right? That will keep changing every time. So it is no longer as clean as this. Okay, it becomes very confusing, right, in the forward view. So then people have come up with a way of implementing the backward view of TD lambda, so that the forward view also stays neat. So they have established exact correspondence between an online TD lambda versus this. I think it is called exact TD lambda or true TD lambda or something like that. I forget the name of the algorithm now, but I'll probably give you a little bit of intuition into that as well when I come to the next class. Okay. Yeah. So let us take accumulating traces. Does that implement first visit Monte Carlo or every visit Monte Carlo? Seems to be like every visit, right? Why do you think that is the case? With a little bit of work you can show that, because I keep bumping this up again and again. So I will compute the return starting from here to here, compute the return starting from here to here again. So I will be using each one of those, right? So you have to look at section 7.4 from the whole book again to figure out how you can write this out, right? Again, it is simple arithmetic. You can write it out so that you can show that the accumulating traces visit implements every visit Monte Carlo. Now it is the interesting question. What about replacing traces? Last visit or first visit?
Last week.
Is there something called last visit Monte Carlo?
Or latest.
Latest visit. Huh? Any thoughts? Any other thoughts? What about first visit? Here is where the section 7.4 becomes your real best friend. It implements first visit. Okay, replacing eligibility traces implements first visit Monte Carlo. Okay, it turns out that when you are showing the equivalence of these two things, right, so these terms telescope into one another, right. So that for the first time you update, you will have VST, then you will have gamma VST plus 1, the next time you update you will have minus VST plus 1 plus gamma VST plus 2 and so on and so forth, right. So these things will start cancelling out, some of these terms will start cancelling out, and because you add a 1 here, those terms do not cancel out, right, they actually each summation keeps going separately, right. So you get every visit, but because I am replace this with 1 here, so whenever something happens again, right, some of the terms in between get cancelled out. So the second time the trace will never start, right, the summation will never start. So it is just the first summation that will keep running till the end, right. This you will understand what I mean only if you look at how the telescoping happens, right. So if more people had put up your hand this morning, this the beginning of the class when I asked you if you have been reading up chapter 7, I would have done that. So I am happy to do the derivation separately for you alone. The rest of the class you have to read up from 7.4, then you will understand what I mean by the telescoping terms cancelling out, so that whatever started from the beginning will continue till the end, right. So it is actually first visit, it is very counterintuitive, and but you have to look at that. So then this is not there in the new book, sorry, new second edition is not there, you have to look at the first edition, that is also available online, right. In fact it is available from the Moodle page, both the first and the second editions are available. Okay, good. So I am actually going to stop here because the eligibility traces for control is a little painful thing. So I will have to let me start it again in the next class. Okay, so next class we will finish eligibility traces for control and perhaps a little bit for off policy eligibility traces. You want Dutch traces? Dutch traces, yeah, Dutch traces is something that came up recently, right. So it is something that sits between accumulating traces and replacing traces. Okay, essentially a Dutch trace I do the update as follows. If beta equal to 1, I get accumulating trace. If beta equal to 0, I get replacing trace. If I put beta something between 0 and 1, I get Dutch traces. Okay. Because somebody from Netherlands published the paper, so it is called Dutch trace. Okay, don't think too much about what is Dutch about it, right? And so it is a Dutch trace, and it turns out that now it gives you an additional parameter to tune, beta, right. But then if you can figure out the right beta for you to use in many applications, turns out to have a better empirical performance than either using replacing or accumulating trace. I mean basically setting beta to 1 or 0, putting some intermediate value of beta seems to give you a better performance. Okay, so there are some hypotheses and reasons as to why this should be the case, but largely the advantage is empirical. I mean, advantage has been established empirically, right. So you don't really have a theoretical reason as to believe one or better than the other. Before we leave, there is one important thing I wanted to point out to you. Gamma is a parameter of the problem. Why? Changing gamma changes the answer. Changing gamma changes the right answer. Lambda is a parameter of the solution method. Changing lambda does not change the right answer. See, the optimal policy is still the same, the optimal value function is still the same. Lambda only lets me have a different technique for measuring or estimating the value function. Okay, whether I take the expected value of GT lambda or whether I take the expected value of GTMC or GTTD, it all converges to the same value function, right. But if gamma changes, the solution changes, right. I can plug in lambda 0.3 here and take the expected value. Truly it should be the same value as lambda 0.6 or lambda 0.9 and so on and so forth. So what I showed you in those curves are because of finite sample sizes, right. If I actually take the true expectations, they will all be the same, right. I showed you for lambda equal 0.8 does better 0.9 because we are working with a finite set of samples. So if I take the true expectations, the answer will be the same. So this is something you have to keep in mind. So lambda is a parameter of the learning process, while gamma is a parameter of the problem, right. And so don't get confused by looking at the backward view. The backward view, gamma lambda always comes together, right. So I do gamma lambda. That's because I want to make sure that when I do the telescoping, things get cancelled out, right. So I have gamma VST plus T VST plus 1 here, but in the next step I will have a minus VST plus 1. I want the two to not cancel out but combine in the appropriate form, so that total when I sum up everything I will get one return, right. So for that I need the gamma here. In fact, in the original version of eligibility traces, original TD lambda algorithm that Rich Sutton proposed, there was no gamma, there was just a lambda, right. And then later on they put the gamma in so that the forward and backward views could be merged, okay.
So, but as we work with the limited samples, so
What's that?
lambda will still affect the solution.
When you are working with limited samples, yeah, because of the process of looking at it, the alpha also affects the solution as we looked at, right. So the alpha is another parameter of the learning process, right. So which is the step size. So the alpha also affects the solution. So likewise, any parameter of the learning algorithm is going to affect the solution because it is going to influence the trajectory you are going to take through the solution space. Yeah, so if you have finite sample sizes, yeah, lambda will affect the solution.